Hello, hopefully the microphone is working okay. Jump straight into it. So GitHub Copilot made this frequency spectrogram view for us. The problem with it is that it's only accessible by a different URL. So not within the same window. So I actually have to go. I have to go to where the URL is /spectrogram. It's actually running. And we'll show the spectrum in a separate Plotly window, which obviously not quite what we want, but yeah, I think that's the whole data loaded, the whole 100 seconds. So you can see the seizure over there. Yeah, the colors are not great. For seizure, you kind of need more focus in the lower frequencies, potentially have the frequency scale logarithmic. Right, so that's how it's loading. Yes, those inputs do not take effect over the spectrogram. Okay, another option. Okay, so we want to show the spectrum in the HTML. So in the HTML, we should have a spectrogram Plotly container. In the plots wrapper, why do we have it twice? There's something wrong with that. Plots wrapper, plot container. We have the raw signal, the frequency spectrum. They have the output container. Okay, this is the wrong place for it. We want it over here somewhere. And we need to refresh this page. Okay, I don't know what that is. We'll sort it out later. Now in JavaScript code, to generate and display the spectrogram, will specifies specifics of your EEG. How do you want to process it? Might need to use a library like SciPy. Once you have the spectrum data, you can use plotly.js to create the plot. Here's the general example of how to do it. We have a get data. We have a fetch data and render. Okay, this is actually changing. Okay, so instead of a separate window, still using a get data. Okay, let's clear this up. Sounds like I need to explain the file first. So it actually goes so that GitHub Copilot has access to it. Okay, then we have the JavaScript. Copilot, explain this. This is mainly so that Copilot has access to the files. We can ask something in line, but wouldn't even know where to start. Okay, so it's generating stuff. So what we want really is have an option to replace the spectrum by a spectrogram, which is much more detailed. Essentially a two-dimensional thing. JavaScript EG data visualization begins, yes. Fetch data and render function is the core of the script. Okay, fetch and render. Okay. And now we have this can't format document. It's configured as formatter but cannot format Python files. Spike formatter. Still a thing. Seems to be. Explain this. Okay, we need to get the names. Do we have a runtime error or something? How's this still working? Right, closing that window didn't stop the app from working. Okay, now it's working okay. Now, the records spectrogram. How to show it in the HTML. We don't want to use an image file. Don't want to spectrate image file. Can convert the basic 64 encoded string embed directly into HTML. To understand, why not just use that's still using an image, isn't it? Can we just use Plotly? Or mat, because we're using both, aren't we? Yeah, this is actually plotting the thing in a separate window. But how about Plotly JS? Yeah, we need to send the data to Flask. So we probably won't be using that, which is okay. It's actually currently working, even though it's displaying the thing in a separate window, but I'll just create a copy for well, actually all the files that we are going to change. And back to the chat. So already have JSON file imported. Now in spectrogram, should be at the bottom here. Just place them side by side for a sec. There's no WAV file. There is no WAV file. It's the data is already loaded. Do you have access to the files or not? Never too sure. Control I. Use that that is already loaded. Yeah, this is hard to troubleshoot this way, but it looks legit. Yeah, it's using the data variable, so we'll accept that. Okay, it's returning HTML and JSON. Let's go back to the chat. So in the HTML, we should already have that min.js. Is that what it's using? Yeah, latest min.js. Why is this script? Why can't just not using JavaScript for this? Don't get it. Why is JS code not in EG.js? Yeah, that's fine. So in HTML, we have a section for the spectrogram plot. Should be underneath there. spectrum plot. Explain this. I'm mainly doing this so Copilot has access to that line. Now okay, how did this JavaScript become so complicated? Spectrum. No, there is spectrum. How about spectrogram? Okay, I'm doing something wrong. Can I just do this control I have to add what did it change? No, that's not what I meant. Okay, it doesn't have the context, this thing. Let's try GPT. Start a new chat GPT-4. And no, that's this guy. It's doing some rubbish. Yeah, confirm reading the code. Don't generate anything yet. Let's see, sometimes it ignores this instruction. Yep, that's good. This one should also have this. Read the code, don't generate anything at the bottom. That's great. We actually have the text to speech running.
I've read the JavaScript code you provided. It's an event-driven script that interacts with the user interface for EEG data visualization, making use of fetch API calls to retrieve data for plotting with Plotly.js based on user input events. It integrates a range of user controls to manipulate the visualization, such as channel selection, window size, and filtering options, and updates information like SNR and MSE dynamically. I have reviewed the Flask application code you've provided. It describes a web service for EEG data visualization with functionality to load EEG data from a text file, filter it using a Butterworth bandpass filter, perform wavelet denoising, and calculate and render spectrograms. There are also routes to serve page templates and handle API requests for fetching processed EEG data. The code includes the definition of the Flask app, routes for serving the main page and handling data requests, and functions for signal processing using Skippy and PYWT libraries. It also calculates the signal-to-noise ratio, SNR, and mean square error, MSE, to evaluate the quality of the signal processing.
Okay, so the main thing is that the spectrogram is not showing in HTML. And let's see what it says.
The issue with the spectrogram not showing in the HTML could be due to several reasons. Here are some potential causes and solutions. Route overlap. There are two routes to spectrogram, which might be causing confusion. Flask might only be using the first one declared, rendering the second one unreachable. Ensure each route in a Flask app has a unique endpoint.
Okay, that's a good suggestion. Yeah, I want to do the second one.
JavaScript and Plotly integration. The display_spectrogram function uses matplotlib to show the plot, which works in a Python environment, but not directly within an HTML page served by Flask. To display plots on a web page, you typically need to use a JavaScript library like Plotly.js, which can be integrated into the HTML template.
Okay, that's good advice.
Data passing to JavaScript. You're attempting to send data to spectrogram. HTML as a JSON string with spectrogram_JSON equals JS onify spectrogram tellist. This data must be correctly handled in the JavaScript within the HTML to render the plot.
Yeah, we haven't changed the JavaScript yet.
Correct use of Plotly in web page. If using Plotly in the web page, you need to write JavaScript code that defines the data structure for a spectrogram and then calls Plotly new plot to render it within a specified less than div greater than element.
Right, have to do that.
Template rendering. The Flask route for spectrogram should pass the necessary data to the template rendering function in a format that can be used directly in the template. Here's a corrected version of your Flask route and an example of how you might adjust your HTML to display the spectrogram using Plotly.
Okay, let's do that. Just go with that one for now. And then in HTML. Wait a sec. So we have one HTML. We should have the file structure. No, we don't have the file structure. The script should be separate. Okay, so first of all, it's getting a bit mixed up. We have the spectrogram plot. Let's do JS first. No, let's do HTML first. Sorry for that. How to change this code in terms of the spectrogram. Then we need to do the same with JavaScript. Yeah, we want to use JavaScript to render it. Here's step by step. Okay, we already did this. Is it the same or changing it again? It's changing it. Yeah, it's actually better because it's not generating an HTML file, it's just generating JSON data. This is better. Yeah, no,
In your script, JS file, or within a less than script greater than tag in your HTML, add a function to fetch the spectrogram data and render it.
Okay, how many web functions? F5. Okay, let's do it there. Yeah, we need to call it.
You can call fetch and display spectrogram when a page loads or when a user interacts with a control that should update the spectrogram, such as the channel selector or a button. For example,
It can just be placed on there after the function. It's not giving me any errors. And in the HTML we have that, oops, division. Yep, that's right.
make sure you have included the script JS file after the plotly latest.min JS script tag in your HTML head or before the closing less than body greater than tag.
Yeah, we should have that. Okay.
Remember to check for any cause issues if you're fetching data from a different domain or port. Since you're likely serving the HTML through Flask, it should not be an issue, but it's good to be aware of it. By following these steps, you should be able to fetch the EEG data from your Flask application and display the spectrogram using Plotly in your HTML page.
Do we need a proper restart? Let's do a proper restart. Don't even see even the placeholder for the plot. Oh, is this clearing them somehow? Use Copilot to explain that bit. Floating elements, property. Just to clear previous floats to understand what it means, but it's probably get rid of it for a sec. Okay, let's go back to GPT. To see the spectrogram. Sorry, super long prompt. Probably get penalized for it. But I need to keep the context intact.
The provided HTML code is set up to work with Flask and Plotly for EEG data visualization, including a spectrogram. However, the code does not include the actual JavaScript that will retrieve and display the spectrogram data. Here's a more detailed explanation on what you can do to fix it. Data retrieval. Ensure that your Flask server has an endpoint that serves the spectrogram data. This endpoint should return JSON data that can be plotted by Plotly, as I described in the previous response. JavaScript integration. You need to have JavaScript code that makes an AJAX call to the Flask endpoint to retrieve the spectrogram data and then uses Plotly to display it. It seems like you have a placeholder for where the spectrogram should be displayed. Less than div id equals spectrogram Plotly div, greater than less than div greater than. But the JavaScript to actually fetch and display the spectrogram is missing or not included in the shared code snippet.
So that's the actual JavaScript. Do I need to change? I think I stuffed something up in it.
DOM content loaded event. You have nested DOM content loaded event listeners, which is unnecessary. You should only need to define it once. The inner DOM content loaded event listener that you have at the bottom of your code is redundant because you're already inside a DOM content loaded event listener block.
It's this bit here, isn't it? Guess do I just remove that? It should be at the beginning of fetch and render. Should be and
Fetching spectrogram data. The function fetch and display spectrogram is defined correctly, but you need to make sure that the spectrogram_data endpoint in your Flask application is set up to return the data in the correct format. Initial call to fetch and display spectrogram. Make sure that the initial call to fetch and display spectrogram uses the currently selected channel value from channel selector instead of defaulting to 0 every time.
okay, so don't need that. Doesn't matter what the function is it? And function should fetch and render should be at the bottom. Place the second function over here. And make a call after the function. And event listener.
Make sure to remove the inner DOM content loaded event listener and use the existing one. Also, ensure that your Flask backend is correctly handling the spectrogram_data endpoint. The function fetch data and render should be invoked within the same DOM content loaded listener, as shown above.
Well, right, it's actually working. It's displaying the spectrogram for the whole 100 seconds. And why the description is overlapping like that?
Lastly, check the Flask backend for any potential errors in the spectrogram data handling and ensure that the endpoint is correctly configured to serve the data. If the endpoint is correct and the JavaScript is properly fetching and plotting the data, the spectrogram should display as expected on the web page.
Spectrogram is displayed okay. But it's using the entire data they loaded. Can just say this because hopefully if it understands the context, it should realize that we want to link to those controllers as well.
If the spectrogram is using the entire dataset instead of the desired window, you need to adjust both your Flask backend to accept parameters for the time window and your JavaScript frontend to send these parameters when making a request. Here's how you can adjust the Flask route to accept the start_second and window_size parameter and use them to slice the dataset appropriately.
Doing the same thing.
When calling fetch and display spectrogram, ensure you pass the start second and window size parameters based on the current position of the scroller and the selected window size. Adjust your fetch and display spectrogram function to include these parameters.
Yeah, it's having all the context and everything, which is awesome.
Then, make sure to update the event listeners to call fetch and display spectrogram with the correct arguments.
So I don't need to do that anymore, do I? If I don't need this. A fast scroller. Do I add it as a right? Let's change it. Okay. Yeah, and select the window size of 100. It should really go to the beginning of the file. Set this to around 50. Well, yeah, it's working pretty well. The amplitudes here. It's the third axis, the color there are auto scaling, but looks pretty good. I had a better one in this EEG review, which was a bit heavy, still loading, but had this nice bit there. It was quite handy. Yeah, that was nice. Yeah, we'll see how we introduce that. Should we get rid of the frequency spectrum? Just take a quick break. By the way, co-authored with GPT. We wrote this blog on the topic of EEG monitoring in the ICU. It's also generated some nice images that don't think they quite look as ICU. There's also not much sense for the screen to be behind the patient kind of thing. But it's a good image overall. And then there's this futuristic looking head stage. Kept asking it to reduce the number of electrodes, but it wouldn't do it. So still resort to how many electrodes it feels like should be there. The text should be pretty decent. We can read it together if you like.
Imagine a world where every flicker of neural activity in a patient's brain is mapped in real time, providing critical care teams with the insights they need to make life-saving decisions. This is the promise of advanced EEG monitoring in the ICU, a frontier of medical technology where innovation meets patient care. In this article, we'll delve into the latest advancements that are shaping the future of neurological monitoring, one waveform at a time.
To reduce the speed by a few notches.
Electroencephalography, EEG, is a non-invasive technique for monitoring brain activity. EEG is used in a variety of clinical settings, including the intensive care unit, ICU, where it is used to monitor patients with neurological conditions such as seizures, coma, and brain death. ICU EEG monitoring systems are designed to be portable and easy to use, with the ability to capture and analyze EEG data in real time. These systems are also equipped with advanced software for signal analysis and trend monitoring. As the medical community's understanding of neurological conditions and brain monitoring continues to deepen, the need for more advanced ICU EEG monitoring systems will grow. This article will explore the future of ICU EEG monitoring and the enhancements on the horizon. Future EEG systems must enhance their ability to distinguish between physiological signals and environmental noise, a common challenge in the ICU. Innovations in artifact rejection and advanced software algorithms will be crucial for improving the accuracy of EEG data interpretation.
Yeah, there's a lot of fluff. It's getting into nitty-gritty, into some technical details over here.
Artifact rejection. Future EEG systems must distinguish more effectively between physiological signals and environmental noise. This improvement would mitigate the interference from other medical devices and patient movement. Advanced algorithms are in development to enhance artifact rejection capabilities, ensuring that the data captured reflects true cerebral activity.
Yeah, there's kind of not much there.
Electrode impedance is a critical determinant of signal quality in electroencephalography, EEG, monitoring, particularly in intensive care units, ICU, where EEG is an indispensable tool for tracking brain activity in patients with various neurological conditions. Impedance reflects the resistance to current flow at the electrode-skin interface, with low levels being ideal for reducing noise and enhancing signal accuracy. High impedance, often due to poor electrode-skin connections, can lead to increased noise and potential misinterpretation of EEG data, making it a significant hurdle in critical care settings where frequent electrode adjustments may be impractical. The quality of EEG recordings is largely contingent upon maintaining low impedance levels, which can be difficult in the ICU due to various constraints. The electrode material, the conductive gel quality, skin preparation, and the presence of hair or dermal oils all affect impedance. While the target is typically below 5 kΩ, achieving this in an ICU environment is often a challenge. Signal quality metrics such as the signal-to-noise ratio, SNR, serve as quantitative measures for assessing the fidelity of EEG recordings, with higher SNR indicating better signal clarity.
Yeah, essentially, generally we're talking about how DSP can improve signal quality. So even if your impedance is too high, you could still get the meaningful signal out of the recording.
Digital signal processing, DSP, is pivotal in addressing high impedance issues, employing techniques that filter out noise and improve the EEG's readability. Adaptive filtering, for example, automatically adjusts the signal's quality, enhancing the EEG by reducing noise that can obscure critical data. Artifact rejection algorithms are capable of identifying and excluding noise patterns that originate from common artifacts, such as those caused by other medical devices. Noise cancellation through wavelet denoising targets high-frequency interference, which high impedance often amplifies, while real-time impedance monitoring enables clinicians to rectify electrode connection issues promptly.
Oh, right. So essentially the speed of DSP processing in ICU should be much faster.
Integrating machine learning with DSP may further revolutionize EEG monitoring by training algorithms to recognize and correct for impedance-related noise, thereby refining the automation of neurological assessments. The employment of these advanced DSP techniques can substantially improve the reliability and clarity of EEG data, supporting critical clinical decision-making for patient management in ICUs. As the technology evolves, incorporating such advanced DSP methods into standard practice will likely become more prevalent, marking a new era in patient care through more accurate and efficient brain activity monitoring.
Anyway, you get the gist. Maybe you could just read it yourself. Should have made a video of how the article was created, actually, but yeah, I did it offline. But yeah, as you can tell, there were extra prompts. I don't remember. I could actually show the previous prompts kind of thing. I'll just do it another time. just jump. We go back to what we were doing. Just realized that some of those controls we don't need. Text over there is really weird. Let's bring the text on the side. Why? Maybe that's what that sentence was there for, this command. And it should be after over here, perhaps. Back this, yeah, clears something, so it is better. Just get read. Oops, just get rid of that. We also don't need log spectrum. Linear log, yeah, could change that scale. Just happen to those. That's displayed. Okay, what? Called elsewhere? No. What's the problem? How to remove I want to remove this second plot while everything else is still shown correctly. Currently it's messing up those numbers there. Don't know what's up with that. Yeah, delete that. Hide the element in CSS. So we haven't touched a CSS file in a while. Just copy it quickly. So what's up? With a couple of options of the element JavaScript. Right, to fix the JavaScript. Don't need that. Okay, that should still. Alright, now this one's working as well. It's good. Yeah, it's a bit grainy. Should be switching. Yeah, the wavelet denoise doesn't do anything anymore. Let's go one by one. What is it doing?
JavaScript control. The state of the checkbox, checked or unchecked, is read by JavaScript to determine whether to include the wavelet denoising parameter when fetching data from the server. Data fetching and processing. When fetching data, your JavaScript code constructs a query string with the current settings of all controls, including the wavelet denoise checkbox. The parameter indicating the wavelet denoising preference is included in the request to the server. Server-side processing. On the server, your Flask application, the wavelet denoise parameter controls whether the wavelet denoising algorithm is applied to the EEG data before sending it back to the client for visualization.
Yeah, it's not actually changing anything.
Wavelet denoising is a signal processing technique that aims to remove noise from a signal while preserving as much of the signal content as possible. It uses wavelets to decompose the signal into different frequency bands and then selectively thresholds these bands to reduce noise. The denoised signal is then reconstructed from the modified wavelet coefficients. The wavelet denoise control allows users to interactively decide whether they want the displayed EEG data to be processed with this denoising technique, giving them control over the level of smoothing applied to the data.
Doesn't actually seem to do anything. JavaScript.
Check JavaScript event listeners. Ensure that there's an event listener attached to the wavelet denoise checkbox that triggers the data fetching and rendering function when its state changes. Verify data fetching includes wavelet denoise. Confirm that the checkbox state is correctly included in the parameters when making the API request. Ensure backend handles the parameter. On the Flask server side, verify that the request parameter for wavelet denoising is being processed. If it's a Boolean value, ensure that it's interpreted correctly. Request arguments are strings by default.
Right. Now it's actually changing the thing. To change it in all the other applications, I think I only have the one. Be back in a sec. Okay, where were we? This wavelet didn't noise thing. Arguments get just find it like throughout the project. Okay, that copy can go. Split up the wrong one. Right. Then I also have it in the noise. We'll set it as well. One run at the moment, we'll assume it's working okay. Not testing is a great idea, isn't it? Well, because we're essentially testing the same thing over here. It's working okay. Now the spectrogram. Is only being affected by the scroller. Frequency scale to change spectrogram y-axis. Should be straightforward, I don't know. Window size HTML. Steps on one, so why? I actually have to click it.
To change the frequency scale of the spectrogram's y-axis based on user selection, you will need to modify both the Flask backend to provide the necessary data in the chosen scale and the front end to correctly render this scale in Plotly. In your Flask route that serves spectrogram data, you might need to adjust the frequency values based on the chosen scale, linear or logarithmic. However, this is typically not necessary to be done server-side since Plotly can handle logarithmic scaling on the client side without requiring any changes to the data. JavaScript front-end to switch between linear and logarithmic scales on the Plotly plot. You can use a JavaScript function that updates the plot's layout to reflect the selected frequency scale. This can be triggered by an event listener attached to the frequency scale select box. Here's how you might adjust your fetch and display spectrogram function to handle changes in frequency scale.
Okay, so in JavaScript, fetch and display spectrogram. After fetching the data,
After fetching the data and within that, then, where you process and plot the data.
is already type in trace. The comma there.
And here's how you might set up the event listener for the frequency scale select box.
Add event listener change function. Instead of that, doing this.
This will trigger a refetch of the spectrogram data whenever the frequency scale is changed. However, if you only want to change the scale without refetching the data, which is more efficient if the data doesn't change, you can simply update the y-axis of the existing plot.
No, it's working okay. Whole spectrum can be removed. Whole spectrum input. Whole spectrum toggle or something. In HTML. Yeah, this bit. Get rid of that. Okay, now we don't see. What? That's not cool.
If you have any JavaScript that handles the state of the whole spectrum checkbox, you should also remove or comment out those references. This could be within event listeners or functions that fetch and process data based on the checkbox state.
This one. Right. That's showing okay. Linear log. Log is default, that's good. Add this filter order was only affecting the EG spectrum. Okay, get rid of it here. The input. Okay, this still doesn't work. Okay, that's working. Yeah, that's okay. That's for the denoising. Frequency scale is working. Where's this coming from? It's like that. Show it. Don't need this. Yeah, log is default. That's fine. Those are okay. Frequency scale is okay. Channel number. Right, now the main thing is the EEG spectrogram. What's this thing called? A plotly diff. JavaScript, we have it over there. We needed to update when inputs change. Currently it's only updating when the file scroller is being used.
To update the spectrogram plotly div when inputs change, you need to ensure that the event listeners for your input controls call a function to update the spectrogram. This function should fetch the latest data using the current settings and re-render the spectrogram plot accordingly.
Yeah, how to do it.
Here's a step-by-step guide to updating the spectrogram plotly div when input changes.
Do I need a separate? Don't think I need a separate thing.
Create a function to update the spectrogram. Define a function that fetches new spectrogram data using the current input values and updates the plot.
I already have a function for that.
Yes, you can use the fetch and display spectrogram function to update the spectrogram plotly div when inputs change. The function needs to be called with the current values of the inputs whenever any input that affects the spectrogram is changed. The function will fetch the appropriate data based on those input values and then update the plot accordingly. The key is to ensure that fetch and display spectrogram is designed to use the current state of all relevant inputs. Here's how you can set up your inputs to call fetch and display spectrogram appropriately.
the whole seizure spectrogram in the frequency domain, by the way. So we really, when we have the window size at the full 100, you should in theory not be able to scroll through the file because it's the whole segment is loaded. And this is how it looks like on different channels. On some channels you see more. On some channels you see less of it. And there's a problem with this one because of that spike there. So also this is updating with input instead of change. Channel selector with change, window size with input. We have the window size, add. Change this to input quickly, just to see. Yeah, it is becoming much slower. And I can hear my server is going. Yeah, there is much more data in there and becomes less responsive as well. I just stick to change. It's kind of nice to see it changing live, but then it's taking a toll on my server. I'll get a huge electricity bill. So I might actually in this spectrogram as well. Yeah, do a change there. Yeah, so I actually have to de-click, release the button, release the mouse button for the changes to take effect, which is fine. Now this spectrogram also should change when you turn the noise on and off. As in you don't turn them on and off because they're both displayed on the EEG signal chart, but for the spectrogram it will display one and then the other. Yeah, that's the linear frequency scale. That's a logarithmic for the seizure on channel 7. That's what it looks like on channel 11. So now a channel, get the picture. So the only thing that is, the only controller that's working with input instead of change is the scroller. Updating the numbers. All other controls, you actually have to release the button for them to change anything. Get the point. Yeah, log log scale for the frequency here is default because you can see better, especially when there's a seizure, what's going on. By the way, this would be the, so this is reloading the page, this is default. This is just showing you the low frequency component because the colors there are automatically scaled. Yeah, it's getting up to 6,000 during seizure and only 1,500 when there's no seizure. Just give me these errors at the edges. We'll fix it a bit later. Yeah, so you see here you have this nice and stable line through the seizures, but that's not always the case. So if you want to train something, a seizure detector algorithm, you will use that line. Problem is, it's not always there. That's the end of the seizure as well. But yes, there's higher energy in the low frequency components, that's for sure, throughout the seizure. Yeah, this channel 7. It's not great as well. Some of them will be better than others. Check something. It shows like the window size. Yeah, that's fine. It's the 3 things that's changing the spectrogram. Yeah, channel number, the file scroller, and window size. And frequency scale, of course, but that's done in a different way. Now for wavelet denoise. Okay, the spectrogram should also be affected by wavelet denoise, because when it's on, it should be taking denoised signal, and when it's off, the spectrum should show the original one. How do we turn this into a prompt? The noise should also affect the spectrogram. We might not prime it with any more information, see if it gets the context and be able to tell straight away if it understands what we mean.
If you want the wavelet denoise control to also change the spectrogram, you need to ensure that the event listener for the wavelet denoise checkbox calls the fetch and display spectrogram function with the current input values. Here's how you can set up the event listener for the wavelet denoise checkbox.
Yeah, I'm not entirely convinced it understands what we are trying to do. Yeah, we already have that, pretty sure.
Make sure that the fetch and display spectrogram function is capable of taking into account the state of the wavelet denoise checkbox. The checkbox state can be included in the fetch request as a parameter, and the server-side logic should then apply the wavelet denoising based on this parameter before sending back the data. Here is a snippet of how the server might handle the wavelet denoise parameter.
Yeah, I'm still not convinced it understands.
With the wavelet denoise checkbox linked to your fetch and display spectrogram function, toggling the checkbox should now update the spectrogram according to the denoising setting. Remember to handle the checkbox state both on the client side, when sending the request, and on the server side, when processing the request.
Alright, so the question is, well, how the spectrogram will update in relation to wavelet denoise on and off. I mean, we know what the answer for that should be. By the way, sorry for that horrible noise. That's a car outside parking. This horrible screeching sound in the suspension, whatever, an old car. To remember to remove it when video editing. Getting back to this. So we asked what will happen when the wavelet denoise input is toggled, how it will change the spectrogram.
The wavelet denoise toggle affects the spectrogram by altering the data that is used to generate the spectrogram. Wavelet denoising is a technique to remove noise from the signal, which can change the appearance of the signal's frequency time representation. When this input is toggled, it should trigger a process that applies or removes the denoising filter from the EEG data and then regenerates the spectrogram to reflect the denoised or original signal.
Okay, so it seemed to be answering more or less correctly.
Every control that affects the spectrogram should call fetch and display spectrogram with the current state of all relevant inputs. This includes the channel selector, the file scroller, the window size input, and the wavelet denoise toggle. After making these changes, test the application to ensure that toggling the wavelet denoise checkbox updates the spectrogram as expected. You should be able to see a difference in the spectrogram's appearance with denoising applied versus without it, reflecting the filter's impact on signal noise.
Right. So we're ready. Yeah, we also want to know why the spectrum looks so granular, so low res. We had something like this in LabVIEW before, so surely, yeah, we could just change the settings. Check it out straight away. Actually using SciPy. What are we using? I don't think we use this function as well, do we? Yeah, this is coming from plot. Where's the PLT matplotlib? There's a function called specgram. This is the one we are using. I don't think so. Surprised we're not using the SciPy thing. Get rid of that. Get this actual function. Yeah, we're using signal spectrogram. Yes, that's what it does. And signal. Okay, it's a SciPy function. It's a MATLAB style IIR filter. Now the actual parameter can be, so it's returning a one-sided, that's okay. As the trend function in build. Yeah, this window. Window. Okay, this is a GitHub Copilot suggesting stuff. That's the segment. Where was it? Window. Optional length of each segment defaults to none, but window is string. What tuple is set to 256? Number of points to overlap. for a window of 10. I have those 10. Yeah, now we have more. Yeah, we could have those parameters potentially as inputs. Anyway, we'll try to improve on this. And we will continue next time. Could add more of these parameters as inputs. Shading is even not in there. Yeah, that's true. Yeah, this window. It's the default option. doesn't seem to change much. Anyway, we'll continue from where we left off tomorrow. Bye.